But it couldn't account for the fact that as soon as any body becomes hot enough to glow, it glows red. Why? Why wasn't more higher frequency, bluer light, radiated as well? In all glowing bodies, why should there be less light at a higher frequency? Intuition told Planck that all could be explained if it takes more energy to make light at higher frequencies. And even though there was nothing in Maxwell's theory to suggest that the energy of light may be related to its frequency, Planck wrote an equation to substantiate his intuition. The energy of light, E, is equal to a constant, h, times the frequency, f. Planck hadn't set out to defy the laws of physics. On the contrary, his intention was to preserve, not destroy, the integrity of Maxwell's theory. And in his effort, Planck saw a solution that happened to be remarkably similar to the solution for that old problem of instantaneous speed. In that case, h was a quantity that would shrink to zero at just the right moment in the calculation. If the same thing happened in Planck's theory, Maxwell's equations would be reconciled with experimental evidence and the radiation problem would be solved. But h wouldn't shrink to zero. Instead of vanishing as he'd hoped, it turned out to have a definite value. And when he found that value, now called Planck's constant, Planck found something more important than an explanation for glowing bodies. He found a new and fundamental truth about nature. Whether by an electrical device or the sun itself, light is absorbed or radiated in discrete bundles of energy. The idea was radical and disturbing, but confirming evidence was on the way. And the evidence can still be seen today in the behavior of a gold leaf electroscope. When the electroscope is charged, the leaf rises and stays aloft until it's hit by a beam of ultraviolet light. An ordinary piece of glass transmits visible light, but it blocks the high-frequency ultraviolet light. When it's interposed, the electroscope doesn't discharge. But when the glass is removed, the leaf falls again. This proves that the ultraviolet light does the job, and it's called the photoelectric effect.